as well as involvement in various scientific missions such as Hubble, the Planck mission, Cosmic Microwave Background, Mars Express, UK's Beagle 2, and of course Rosetta. So I'm not going to spend much longer than that in introducing Nigel. I just turn it up, but I would just like to note two things before I hand over to Nigel. In January, we have a lecture on the Ediacaran, Biota and Charnia fossils. Oh, that's Professor Alex Liu from Cambridge. And in February, we have beer. We have Timothy O'Rourke talking about the role of evolution of yeast in brewing. So I think I'll turn over to you, Nigel, and let you carry on.
Okay. Well, hopefully you can all hear me. Thank you very much. Thank you. So this evening I'm going to be talking about EarthCARE, and this is the word EarthCARE, as you might imagine, is to do with the Earth and to do with observing the Earth from a satellite in space. And this satellite is now actually in orbit as of May this year. So it's a very timely point to discuss the mission. And when I first heard these words, it was probably, well, it was nearly 20 years ago. So it's been a long path to get to this point and have the satellite in orbit. So behind me, you can see two mission patches. So not every mission has two mission patches, but this one does, and I'll explain why in a moment. And you can see some happy faces in the upper right, including mine, when the instrument was integrated on the satellite some years ago, and it's been waiting for launch for the last few years. And you can get an idea of how big it is. In fact, I managed to bring along this model, which is a full-size model of the broadband radiometer, which I'm going to be talking about. Is the contribution, or the main contribution, that came from the UK. And you can see that the real one, the real flight instrument, is in the lower right-hand picture. So why have we got two mission patches? Well, the answer is it's a joint mission between the European Space Agency and the Japanese Exploration Agency. So we have an ESA mission patch in the upper one, and a Japanese one with a nice white dragon in the lower window. So hopefully this will play when I click on it. Yes, here we go. Okay, I left talking over the top of the video so in case the people on Zoom wouldn't be able to hear. So what you saw there was a satellite and a white dragon. The Japanese love dragons, so they had to get a dragon in there somewhere. And you can see from the shape of it that it resembles a dragon, with the solar ray being the tail of the dragon. So there's some physical similarity between the white dragon, which is what Hakuryu, apologies to any Japanese speakers in the audience, Hakuryu means in Japanese, apparently, white dragon. So there's a physical similarity. You can also see the satellite in the video was white. This one isn't. And the reason for that is this is a very old model. And the design evolved over time, and it was decided to cover it in a material called beta cloth, which is this white material that you saw in the video, which is similar to what people wear on their spacesuits. It's It's a man-made synthetic fibre covered in PTFE. And the reason it's attractive to use it is it resists atomic oxygen. Now, someone, when they walked in, was talking about aerodynamics. Well, actually, there are aerodynamics at 400 kilometers even. The atmosphere is very thin, but one of the reasons the spacecraft has a trailing solar array is it's traveling in this direction and it needs to minimize its cross-sectional area. So instead of having the solar array sticking out the side, as you probably used to seeing a satellite, this one has a trailing solar array to minimize that atmospheric drag and prolong its life. So, and one of the other things you have at 400 kilometers altitude, which sounds quite high, but it's low in terms of spacecraft, is atomic oxygen. Because although the atmosphere is very thin, you've got atomic oxygen and it's highly reactive. So it will chomp through a lot of materials that your spacecraft's made of. So covering it in this beta cloth material, which is silica fibers coated with PTFE, affords it some protection. And in Japan, dragons are revered as divine creatures. And governing water, and that's one of the things I'm going to be talking about, because water and ice are key to what's going on in clouds. So there's a connection there with the white dragon, and so we'll talk more about that in a moment. So let me move on. So EarthCARE, as I said, was launched earlier this year. It went up on one of Elon Musk's Falcon 9 rockets after many, many years. And you can see it there on the launch pad a few hours before it went up. And this has got a very strong connection. This satellite and the project has a very strong connection because of the team that worked on it in Bristol, of which I was part of. So it's got a local connection and it goes back a long time. So I'm going to be talking about some of the history as I go through this as well. So just to sort of give you an outline of what's going to happen ahead, I'm going to start off by talking about the mission and the science. So what's EarthCARE doing? And then I'll talk a little bit about the satellite and then the instruments in particular. It's carrying 4 instruments on board. The broadband radiometer, which was the one that was designed and built in Bristol, was one of those 4. What the Bristol team was involved in the mission, what they were doing, a bit about the history and why it's taken so long, which I'm sure will surprise some of you. And then touch briefly on the launch earlier this year and what we've learned so far after the first 6 or 7 months in space. So EarthCARE, of course, stands for something, and it stands for Earth, Cloud, Aerosol and Radiation Explorer. It's a joint mission with the Japanese Aerospace Exploration Agency, and it's the 6th in a series, the 6th Earth Explorer in a series of spacecraft missions, which are called collectively the Living Planet Earth program. And it's fair to say it's probably one of the most complex Earth Explorer missions that the European Space Agency have done to date. And that's part of the reason why it's taken so long, more of which later. So a little bit about the science. I'm not a climate scientist, but let me tell you, and I'm sure you can appreciate some of this from your own everyday understanding of how things work and your experience of nature. So clouds are absolutely have a central part to play in how the atmosphere heats up and has an effect on our climate. And it's one of the biggest uncertainties of understanding the climate is what's going on in these clouds. Now, clouds have a couple of major effects. One is that a big cloud, like a cumulus cloud, will reflect a lot of solar energy coming from the sun, which is good in terms of cooling, but they also trap a lot of infrared heat coming up from the surface of the Earth as well. So clouds can act in two ways, and it's not always obvious which one is going to win. So it's all about understanding whether there's a net cooling or a heating effect going on, and understanding what the clouds are and where they are, what their altitude is, what temperature they are, how dense they are. So, you know, cirrus cloud is going to be much more going to pass a lot more energy through to the Earth than a cumulus cloud. So so water and ice in these clouds will influence what's going on in terms of the way the climate's affected. And that's what this mission is trying to get an insight into. Now, aerosols, which is the A part of the EarthCARE bit, these are tiny particles such as dust and pollutants, and these are suspended in the atmosphere inside a cloud. And they're also having an effect in terms of reflecting and absorbing solar radiation. Aerosols also act as somewhere that clouds will seed on. So clouds will form if there's some particles they can seize on. And that's one of the biggest influences on our understanding and on our climate, is how aerosols affect the formation of clouds. And then lastly, of course, we know that concentrations of aerosols are driven by what we as humans are doing on the surface of the planet. So, and that's not a situation that's improving particularly at the moment. So the last sort of bit of the science I'm going to talk about is the what's called the radiation budget, and this is the balance, if you like, in terms of auditing the amount of heat arriving or amount of energy arriving from the sun with what's able to leave the surface of the Earth, and that obviously determines whether the planet's going to be warming up over time or cooling down. And clouds and aerosols, as from what I've already said, you can see they will have an impact on this. So let me leave that there for the moment. I'll talk a bit about some of the results at the end. Let's have a look at the satellite. Now I've got a model of the satellite here, which is a 1/20th scale. So Buzz Lightyear here is about the right scale if he was about 1.6 meters tall. Now it's in a sun-synchronous orbit, a polar sun-synchronous orbit. So as you might notice from the video, the Dragon and the spacecraft are flying over the poles. So that's what a polar orbit means. Now, what does sun-synchronous mean? It means that as the Earth goes around the sun during the year, the plane of the orbit of the spacecraft precesses at exactly the same speed. So it's always looking at a scene on the ground in the same sunlight conditions. So this makes it easy to compare data taken 1 week or one orbit to another orbit. It's doing 15 orbits a day, so it's doing a lot of spinning. It's a 25-day repeat cycle. So if you can imagine, the Earth is rotating underneath the satellite as it's flying around, and 25 days later, the spacecraft is passing over exactly the same point on the ground again. So you can build up a complete picture of the Earth's surface, or the clouds, I should say. Most of these instruments are measuring what's going on in the clouds rather than the surface of the Earth, every 25 days. Now, the descending node, 2 o'clock in the afternoon, that is the time at which the satellite crosses the equator when it's going down towards the South Pole. So 2 o'clock in the afternoon. So this is what I mean by the sun synchronous bit. It's always 2 o'clock in the afternoon as it crosses the equator heading south. The solar array is 21 square meters, which is a sort of reasonable sized solar array for a satellite. The spacecraft weighs 2.35 tons at launch, which again is a sort of, you know, normal sort of spacecraft size. I mean, it's not a small satellite, it's quite a big one, but not massive. And it's designed for a 3-year in-orbit life. And we'll talk about some of the things that limit the life, but propellant's one of them. Life of the mechanisms is another. Mechanisms in space are, as I'll tell you later, can be a bit of a nightmare because it involves things moving, and lubrication tends to evaporate in a vacuum. So that's quite a challenge. It's carrying 4 scientific instruments, and I'll talk about those on the next slide and the subsequent slides, of which the broadband radiometer is one of them. It's downlinking data of 2 megabits per second. Again, this is over ground stations. So it stores the data on board, and then as it passes over a ground station, say northern Sweden is a common one, it will squirt the data down to the ground. Now, originally, this was going to go, I'll talk about the launch date later, but originally it was going to go on a Soyuz Fregat launcher. Now, these are Russian ICBMs, left over from the Cold War. They're nice and cheap, they're pretty reliable, but they come from Russia. So ever since our friend marched into the Ukraine, Europe's had a slightly different attitude to using a Soyuz launcher, quite understandably. So a couple of years ago, there was a decision to change and look at other launchers, and eventually the decision was made to use a Falcon 9. So that's why we've got a couple of years delay at the end of this process. The spacecraft was all ready to go 2 years ago, and then someone decided to march into the Ukraine. These things happen. So looking at the satellite, don't bother reading the labels on this one. I just couldn't get a picture without them. But essentially, it's divided into 3 parts. Let me point on the screen. So the first part is this big dish you can see on the end, which is over 2 meters across, and has its sort of bit that doesn't move. This is folded against the side of the satellite for launch, and then it opens up once you're in orbit. This is the main reflector for the radar, and this is the bit that comes from Japan. This is the cloud profiling radar. So this top of the satellite is the cloud profiling radar. Then you've got a segment in the middle, which is the ATLID instrument. This is the lidar. So this is pulsing laser pulses into the cloud. And this is the middle section here with this big baffle you can see at the bottom. You can see me pointing, yes. And then the lower part is the sort of spacecraft platform with the usual batteries and everything else, the solar array connected to it, and the other 2 remaining instruments, the broadband radiometer being one of them, and the multispectral imager. So I'm going to talk about all of those now. So I'll start off with the ATLID instrument. So ATLID stands for atmospheric lidar. Now, a lidar is like a radar, and it's operating in the visible wavelength spectrum, and it's emitting pulses, laser pulses at 355 nanometers. So that's in the ultraviolet. And what it does is it, by sending these pulses into the cloud, you're able to measure when you get the reflection back from, if it hits an aerosol, interacts with an aerosol or a dust particle, you get a reflection back. And by knowing how long that's taken, speed of light, that tells you how far below the spacecraft it is and how deep in the atmosphere it is, and where it sits in the cloud. You know, is it in the middle of the cloud? Is it at the bottom of the cloud? So this is a very complicated instrument. It's firing these pulses into the clouds. It's a big instrument. It's over 0.5 ton. and it consumes nearly 500 watts of power, which doesn't sound like a lot of power probably to a lot of you, but that's quite a lot of power in space. You know, you've probably got maybe 2 kilowatts, 1500 watts available to the whole spacecraft. So that's using quite a big proportion of it. Now, the prime contractor for this instrument was Airbus in Toulouse in France. And in Bristol, we provided the instrument control unit. Sorry, there's lots of acronyms in here. I've tried to put the most important ones at the bottom of the slides. The instrument control unit you can think of as the computer that controls the instrument. It has the software for the instrument running on its processor system inside, and it has all of the electronics to take the data, control what the instrument's doing. So hardware and software. Let me talk about the next instrument, which is the cloud profiling radar. So this is the one that came from Japan. It's operating at 94 gigahertz, which is about 3 millimeter wavelength. So it's a millimeter wave radar. And again, it's sending pulses into the clouds. And it's looking at the Doppler shift on these pulses. So it's not only measuring when the reflection's coming back, but it's also looking for any changes in frequency from the one you've sent down. And that tells you, you know, about the speed of the particles in the cloud. It's a big instrument again, 270 kilograms, 340 watts, built in Japan. Part of it was built in Germany by Airbus in Friedrichshafen in southern Germany, and part of the quasi-optics. Maybe I should explain what the quasi-optics is. This is like the optical part of the radar. So, and it basically works like in a similar way you'd have mirrors in an optical system. You have quasi mirrors, which are reflecting this 3 millimeter wave microwaves. And part of this was built by the team in Bristol, what was called the quasi-optic receiver and transmitter flip mirrors and the electronics associated with those. And these were for redundancy, for switching between the prime transmitter and the backup transmitter, and the same for the receiver chain. So it gives you some redundancy, which is always important in space because you can't maintain it. The multispectral imager is a passive instrument. So this instrument and the broadband radiometer, which is coming up next, these are just measuring radiation coming up from the top of the atmosphere or from the ground if there's no clouds. And they're measuring, so it's what's called a passive instrument. It's not sending any pulses down. It's not an active instrument. It's just receiving whatever's coming up. MSI is measuring in 7 spectral bands across the visible and into the thermal infrared, so out to about 10 microns. And it's giving you a picture. That's probably the best way to think of it. It's giving you like a picture, an image of what the other instruments are looking at. So it gives you some context for understanding what the radar and the lidar are seeing. You can see there's a cloud there. You can see what type of a cloud it is. So a smaller instrument, 56 kilograms, 59 watts. This instrument was led by a team at Surrey Satellites in Guildford. So good UK contribution. And their instrument control unit was also provided by the team in Bristol. And I'll talk a little bit about why this happened later on. Right, the last instrument was my broadband radiometer. This is measuring radiation in across a very long, a very broad band, which is why it's called the broadband radiometer, all the way from 0.25 microns out to 50 microns. Now that's 2 orders of magnitude, and probably so a lot of you can appreciate that's quite a challenge to do that in one instrument. Now, the way we do this with the VBR is we're looking at these fluxes, which are usually originating from the top of clouds, so it's the top of the atmosphere. Essentially, we're measuring it in 3 directions. We've got three telescopes inside here. If you think of the Earth being that way, you've got the telescope in the middle that's looking directly at the point below the satellite, and you've got one looking, let me get this right around. The forwards telescope is this one looking that way, and the rear telescope is looking that way. Now, what happens, and I'll talk about this a bit later, is on the next slide, in fact. So you're looking at plus or minus 55 degrees ahead and behind, and straight down to what we call nadir, immediately below the satellite. And we're doing this in two bands. So we're using a quartz filter to give us a short wave, which means anything shorter than 4 microns is transmitted through quartz. And that gives us our shortwave signal. And then by having no window, just an empty space in the instrument, so it passes all of the radiation through to the detectors, that gives you what's called a total wave. And we can arrive at the measurement of what's happening between 4 microns and 50 microns by subtracting the two, essentially. Sounds nice and simple. It's all done on the ground rather than done in the instrument or on the satellite. But I'll talk a bit about that later. And this again is a 47 kilos, 32 watts. So it's the least massive of the instruments, the 4 instruments, and the least power. And this is the instrument we were responsible for in Bristol as the prime contractor. And I will talk about in detail later, but what you see in front of you is a full-size model of the optics unit. So this is the bit that's sitting outside the satellite. On this model, it's the bit underneath a model hanging down, sticking out. That is you'll see it, maybe come and see it at the end, but that is the BBR on at the 20th scale. Right, let me move on. Right. So this is showing the geometry. So you've got the plane of the Earth below. The satellite is this represented by up here with these 3 telescopes in yellow that I was pointing out on the model earlier. And the spacecraft is flying in this direction. So you've got a forward-looking telescope, a telescope looking towards the nadir, and one looking backwards. Now, what's happening as you're making these measurements from the instrument's point of view, the Earth is rotating underneath, which is a bit of a nuisance, but it's all part of the situation. And these measurements are being taken approximately a minute apart. So the Earth is rotating a little, but enough that you've got to be careful how you compare the data. So what we have is not 1 pixel in our detector. We have a 30 pixel detector array, which is able to give you a scene with some width. And then as you view the images in this telescope, they gradually move across the detector array. So you can reconstitute this on the ground by picking the right pixels to extract your data. Right. And at the end of the day, to give you an idea, these pixels are looking at maybe 600 meters on the ground. I mean, hopefully it's looking at clouds at the top of the atmosphere, but if you're 393 kilometers up, then whether the clouds are a few kilometers ground level or 10 kilometers, it's a long way from the satellite. So 600 meters thereabouts, and you're summing those pixels to make a 10 kilometer square image. That's what the scientists wanted out of this instrument. So on this slide, you can see, recognize a bit more about the optics unit. I'll show you the other side briefly. It's not as interesting. It's basically a radiator with the back of the mechanisms and the electrical connections on it. This big panel is a radiator to get rid of heat. So one thing you want to do if you're a radiometer is keep your detectors and the enclosure of the optics as cold as you can get. Now, what do I mean by cold? Well, I don't mean cryogenic. I mean -10, -20 degrees, because the coldest cloud you're looking at is probably -10. So you need to be colder than the scene you're looking at, essentially. So this is it's not easy to see it, but it's actually configured in two halves, which are sort of nested inside each other, which is a bit hard to tell from the outside. But it's essentially a telescope assembly with the optics and the detectors in it primarily, and then what we call a mechanisms assembly, which has a chopper drum mechanism, which is rotating at constant speed, and a calibration target mechanism, which moves every few minutes. And I'll describe this in more detail in a moment. Now, these elements were designed and built by other parts of the UK consortium that we put together. The Rutherford Appleton lab, not so far from here, near Harwell, provided the telescope assembly, and the mechanisms assembly came from a company called ESR near Warrington. And the whole optics unit was put together in RAL's facility, and on the picture you saw on the cover slide at the start was in the RAL clean room. So that was done joint team between RAL and the team in Bristol, the integration of the two halves. Right, what you're looking at here is a cutaway. So I've taken a big slice through the optics unit so you can see what's inside. And you can see the three telescopes, these three baffles, the nadir baffle, the forward baffle, and the rearward baffle. So the three baffles are the telescopes. And then in the middle, in this ring here, you've got what's called the fixed optics assembly. This is the bit that doesn't move. The baffles don't move at either, but the bit in between this ring and this ring is the calibration target mechanism that rocks backwards and forwards. It doesn't go round and round because it's got a flexible harness across it, like a printer cable. You can imagine one of those. And what you can see is four black bodies. These black bodies I'm pointing at, which you might be able to read the words on. So these four here, and two of them are hot, say at 20, 30 degrees centigrade, and the other two are cold, -10 degrees centigrade. And these have to be moved in front of the telescope and their detectors every couple of minutes, or every 90 seconds, in fact. And this is because we can't really control the temperature of the radiometer accurately enough, as it flies around the Earth. It's influenced by whether you've got cloud there or not below, in terms of the heat coming up from the Earth, and also whether it's day or night. Because at some part of the orbit, we are behind, with the sun the other side of the Earth, so we're in darkness. So this obviously has an impact on the thermal stability of the instrument. So we have to regularly, every 90 seconds, recalibrate the detectors. So we have to move these black bodies backwards and forwards in front of the detectors and their telescopes. The other thing this drum is doing is it has some mirrors on it. Now, I mentioned that the spacecraft's flying in a polar orbit. When it flies over the South Pole, the spacecraft actually, the sun appears over there on this satellite model. This baffle here is looking alongside the solar array, not at the solar array, but in that direction. And it's looking at the sun for about 20 seconds. And I'll describe this calibration in a bit more detail later. But this is another part of this part of the instrument design, is to introduce that the sun as a solar calibration source as well. I should say the chopper drum, which is sitting in between here and is moving around at constant speed, I'll show you another picture in a moment, has two empty apertures and two apertures where you have the quartz filter fitted, so that it's chopping the signal and giving you this different radiation onto the detector. And that's going around at constant speed. To talk about the detectors for a moment. So these detectors are microbolometers. So they're effectively measuring heat, although it's heat that goes into the ultraviolet, through the visible into the ultraviolet. But it's measuring radiation, and the pixel size is about 100 microns. So you've got a electron microscope photograph here, and that distance is 100 microns, so 1/10 of a millimeter. And they're special because they have to absorb radiation that falls on them across that huge wavelength range. And what they have, and I couldn't find a picture of this, but it looks like it's called, well, it's vapor deposited gold black. People don't normally think of gold as being black, but if it's in very small strands, and it looks like it's all, if you look at the surface of the detector, it looks like it's hairy, and it's growing these sort of strange tendrils and so on. And this is one of the reasons why it looks so black, and why it can absorb all the radiation that falls onto it, because nothing is reflected back. In this image here, you can see this funny sawtooth arrangement, and this is showing the voltage on the detector signal. So as you come to an opening in the chopper drum, which is what's represented up here in this upper image, you can see the signal on the detector rises and then starts to fall again as the window closes, as the chopper drum moves further and the window starts to close. And this repeats. So this is what's giving you the chopped signal, which is central to the way the instrument works. So to look at what's going on with the chopper in a bit more detail. So the chopper drum's rotating at constant speed. It's just over 4 Hertz, 261 RPM, which is important because it's basically having to do that for 3 years continuously. And if you add up the number of revs, it's something like over 400 million revs, which probably isn't a significant issue for a mechanism on the ground, but it is a big issue for a mechanism in space for the reasons I mentioned earlier. So we'll talk a bit about that, more about that later on, the mechanism life, because that was one of the central problems we had on this instrument. So in the lower image here, you can see a bit more clear what's happening when this. So when the empty aperture on the chopper drum is aligned with the telescope and the detectors, you get this total wave signal building up. It plateaus as the window is perfectly in position, and then starts to fall as the window closes. And you have a lower signal, of course, for the short wave, because it hasn't got the 4 microns to 50 micron radiation falling on it. That's blocked by the quartz. And on the left, you can see a bit more detail. So you can see the chopper drum here, and this is a quartz filter in sort of 3 segments on one of those windows. We talked a bit about the calibration earlier for the total wave in terms of these black bodies. So these are items that have a very well-known temperature. They've got platinum resistance thermometers, or more than one, in fact, on them. So you know exactly what their temperature is. You've characterized them on the ground. So you know exactly how much radiation they're putting out at a certain wavelength. So these are a very good calibration source. The only trouble is with the demanding instrument, the thermal stability requirement, you need to use them on a regular basis every 90 seconds to keep your detectors have a known calibration. The other thing that the calibration drum does is related to what we call FDIR. So this stands for failure, detection, isolation, and recovery. So if you have a thruster that's stuck on the satellite, and the satellite starts to change its attitude, it may, worst case scenario, introduce the sun into the baffles of the instrument onto the detectors, which for this instrument would completely kill it. So the calibration drum is able to close off and protect the instrument detectors in the case of an attitude anomaly. So that's an important feature again of this drum. Right, a few moments on the visible calibration. So this is the one using the sun. Now, we're not doing this anywhere near as often, nowhere near 90 seconds. It's about every 2 months. And for every 2 months, we have every orbit, and it says 30 orbits there. So that's 2 days worth of orbits. So every orbit in that 2-day period, every 2 months, you take a calibration with the sun. And you can imagine the sun passes into that baffle, calibration targets move to the right position, and the light from the sun hits a diffuser. It doesn't enter the optical chain unprocessed. It illuminates a diffuser, which then scatters light in a particular way into the detectors via the telescopes. So this is used to look at the aging of the system. It's used to see if there's any movement in the calibration of the visible part of the system. Right, the instrument control electronics. So for the BBR, it's a unit in 2 halves. So you can see there's, in this image, there's basically this middle position here, and you've got the same electronics boards either side. And it's cold redundancy, what we call cold redundancy. So you've got one half that is on and the other half is off. Hot redundancy is when you've got both halves on, but we've got cold redundancy. It has a common architecture with the other instrument control units for ATLID and for MSI. And in particular, the processor board is identical apart from the application software, which is unique to the instrument, but it has the same boot software on. Now, why is this a good idea? Well, you think about it, the spacecraft has an onboard computer, which is the main computer in the spacecraft that's controlling the whole spacecraft as well as the instruments, talking to the 3 instrument control units and the equivalent of the Japanese instrument as well. So it's taking the telecommands coming up from the ground that come in through its communication subsystem and relays them to each of the instruments as needed, or to other parts of the satellite. And that works over a 1553 interface, what's called a MIL standard 1553 interface. So, and this is the same for each instrument. So having a common design for all of them de-risks the project in terms of, you get it working for one, it's going to be working for all 3 because you're talking to the same on-board computer. Similarly with the mass memory and formatting unit. Now, the mass memory and formatting unit is like the data recorder on the satellite, only at solid state now rather than tape. And that is taking all the science data, which is coming from each of the instruments from their control units, and storing it on the satellite before you have a pass over a ground station when you can squirt it down. So that's why it's a good idea to have a common design, and I'll talk a little bit more about that later. And the electronics was one of the things we designed in-house with the team in Bristol. We had a team of 8 or so electronics engineers and a software team in CSTS in Bristol as well, who were doing the software. So I'm going to talk a little bit about what we did in Bristol now. So as I said, we were what's called the instrument prime contractor for the broadband radiometer instrument. And we worked with these other companies that I think I've mentioned on the way through, CSTS being one of them. And we also had a company called Spur Electron in near Southampton, who were responsible for buying the EEE parts. So these are the electronic parts that we have to use, which are very specialized for space because of the radiation environment. So they're like military parts, but even more special and expensive. So this amounted to something like over 30 million euros in terms of value, which was about 10% of the satellite cost, including the instruments. So it's quite a significant part of the spacecraft we were entrusted with. The little footnote down there says TAS UK acquired the SEA Space Division in 2015. So they changed the name over the front door of the company at one point. Most of the project was completed prior to 2015. So essentially, this project was done under the auspices of Systems Engineering and Assessment Limited in Bristol. But the final stages of the contract were completed as part of Thales Alenia Space UK. Graphically, you can see here, this is the contract for the satellite in this box at the top. Airbus in Germany with a prime contractor for the satellite. And these are all the different parts of the satellite. I've ringed the bits that we were responsible for on these 3 instruments, as you can see here. So this is the BBR segment here. This is the big ellipse. And then the 2 smaller ones are for the instrument control units for the other 2 instruments. So it's a significant part of the satellite. That doesn't include the Japanese part as well, because that's not part of the European procurement, of course. So a few minutes on the history, and then we'll head towards the end. So in 2006, we had a study in the UK, which was funded by the what's now called the UK Space Agency, and we had a series of meetings in industry to see if we could form a consortium to build this instrument, which is what we did. At that particular time, there was an under-return to the UK from the European Space Agency. This is a measure of the UK contributes so much money to the European Space Agency, they take their cut, and so much money comes back to the UK industry in return. And this under return is a measure of how poorly the UK industry was doing at that time in terms of winning contracts. So the idea that we had at that time was to address that by give the European Space Agency a solution where it had a lot of UK content, not completely UK. The detectors came from Canada, for instance, and the EEE parts came from all over the world. So in 2007, we started preparing a proposal. So this is, you're probably not familiar with the process, but essentially you have an invitation to tender issued by the European Space Agency, and then industry has to respond to that in terms of, this is your specification, this is what we can offer to build for you, how much it'll cost, how long it'll take, etc., etc. Now, at that time, rather we had a rather special circumstance where the industrial main players, which were Airbus and Thales Alenia Space, basically came to some agreement and said, well, you bid for that satellite and we'll bid for this satellite. So the European Space Agency were rather disappointed when they only got one bid from Airbus for EarthCARE. And inside the Airbus consortium, they'd already said, well, we'll have our part of the company, Airbus in Portsmouth, and they'll provide our BBR solution. So we had a situation for the team in Bristol. We were preparing our bid, and we had effectively a prime contractor for the satellite who wouldn't give us an invitation to tender. We were excluded from the contract by their action. Now, that's not where it ended up, of course, but it was a struggle, and we had to argue. We had some very difficult arguments with the European Space Agency and with the UK Space Agency to be allowed to bid for the broadband radiometer. And ESA eventually turned around to Airbus and said, look, you've got to let these guys put their bid in. It's only fair. And what's more, because you've got your own company in the UK providing a bid for this instrument, we'll have to evaluate the bids. You're cut out from evaluating it. So ESA evaluated the two BBR bids, one from Portsmouth, one from Bristol, and we won the competition. And here we are today. So this was a very happy part of history, as I remember. So we had the eventual contract award. Everyone got over their hangovers, and then we started work. And phase B started in 2008. So phase B was about a year and a half, and this was the design phase, when we had to do all the engineering and decide what it's going to look like, where we're going to buy our parts from, and so on. In 2009, we had our preliminary design review for the instrument and also for the satellite. And then we had this conversation in 2010 about could we make the ICU design common to all three European instruments and get some benefit from that in terms of lower cost to the customer, of course, and lower risk to the customer with commonality of the designs, only having to do the design once. So this is how it turned out. In 2012, we had our critical design review, which is where you have a gate with the customer and say, right, we're going to go and make the flight model now. So this is committing to the expensive part of the program. And then we delivered our instrument in 2018, as you saw on that picture, and you can see on the image behind me. And there's the BBR instrument on the side of the satellite. And look, nothing else is on the satellite yet. What a surprise. We were the first. And then, as I said earlier, we had a change of launcher in 2022, and 2024, we had in May, we had the launch, finally.
Where's Vandenberg?
Vandenberg is on the west coast of California. So it's got a lot of sea to the west of it. So if you launch to the south, it's deemed to be safe unless you're a whale or something. The original launch date when we signed the contract was 2013, and here we are in 2024. So what's happened? Where did it all go wrong? Well, as I said earlier, that it turned out to be a much more complicated Earth Explorer mission than was originally foreseen. So, and in particular, not wishing to point any fingers or mention any names, but the two complicated instruments turned out to be a bit of a beast. And that was the ATLID instrument, the lidar and the radar in Japan. And they were delayed by many years, both of them. In the case of the BBR, we had a problem with the chopper drum bearing life, which I alluded to earlier. It's common in these situations to have a life test, what you call a life test. So this is where you have an accelerated life test to demonstrate the bearing life. And we had 3 of these, which failed. The last one it wasn't deemed to be a complete failure. It was deemed to be good enough, but it meant that the life might not last the full 3 years at the nominal 261 RPM. So what we introduced as a result of that was a programmable speed. So we could lower the speed of the mechanism and reduce the number of revolutions if it started showing signs of aging. Now, so far, it's all looking fine, but we are notionally running at about 3/4 our normal full speed. And because we can still do science at that speed, the instrument still works. So this is the way we've dealt with this, rather than go through another design iteration, because it's recognised as being quite a high number of revs for a space mechanism. Right, enough of that. What you're seeing here is a real image of the spacecraft leaving the top of Elon Musk's rocket, thank God. And you can see 10:46, 10:47, 10:48. That's minutes and seconds after the launch, after liftoff. So it doesn't take long to get into orbit, because you move pretty fast. And on the right-hand side of the image, there you can see the baffle, the Vizcal baffle. There it is, there. So that is what you're looking at here, just peeping out. So it's not often you get to see a bit of your hardware in space actually leaving the rocket, but there we are. I think that's the first one I've ever seen. Right, let me finish off by discussing a few of the results. There's not been, with the instruments, well, the whole satellite and the 4 instruments take several months to commission when we take the first images and check out how everything is working. And there's a process, a validation process, which has begun, and in some cases involves flying aircraft with similar instruments over the same clouds that you're able to image with the spacecraft. Now, the spacecraft's moving a lot faster than an aircraft. The spacecraft's moving at 7 kilometers a second, so it's streaking across, but nevertheless, you can fly an aircraft in. Now, when I gave this talk a few months ago, someone asked me, can you see aircraft contrails on these with these instruments? And I said, that's a very interesting question. I don't know. Well, the answer is yes, you can, because in this image here, you can see 2 aircraft, and in the you can see this yellow one here is sort of flying around a horrible, I don't know what the pilot would, smoking, but anyway. And then there's a blue track, which looks a bit more sensible further down here, which is a bit less convoluted. Anyway, those are 2 aircraft, and it's their contrails that the CPR radar is able to see. It's able to see the water vapor from those 2 aircraft. Anyway, that's just an aside. Now, what you can see in this image here, on this, where's my cursor gone? Oh, it needs to be pointing at this part of the screen. Yes. See this image here is the CPR, and it's like taking a segment looking through the cloud. It's a vertical segment looking down. So it's using this time of flight to measure where it's getting the reflection from. So you can see the structure inside the cloud. And there's some, yeah, there's the top of the cloud in this part of the image, which is being measured by the lidar. So let's have another look at the next image. So what you're seeing on this one is, so it's the EarthCARE satellite in the top strip, and you can see some structure here from the clouds. Altitude on the left-hand scale, so this is about nearly 15 kilometers altitude. And it's comparing that with the instrument flown in the aircraft in the lower image. And so the scientists are looking at the two instruments, one on the aircraft, one on the spacecraft, and comparing them to see what's going on. Right, I think my voice is about to pack in. But let me show you one more picture. So we're just about at the end of this commissioning period. We've just had these validation flights. There's a workshop in January with all the scientists to discuss the instrument measurements to date, but that's in January, so I can't talk about the results from that. Yeah, so this one is showing so this is the spacecraft flying this strip here, and this is over, let me get my orientation right. Yeah, so this is northern Italy here. So you've got the boots on the, sorry, I'm pointing at the wrong screen again. This is Italy, and the boot is down the bottom here where it says thunderstorm. And you can see some of the radar results here. You can see this big, heavy rain and hail. You can see the difference between them, in fact, with the radar. And this was a storm that was causing severe flooding at the time. Storm Boris, there we are. It says it all, doesn't it? Okay, anyway, let me pause at that point, and I will move to Barbara. I apologise in advance for this, but you set me a challenge. And this was the best I could come up with, because I know you were expecting the Star of Bethlehem, and this isn't the Star of Bethlehem. But anyway, so my question to you, and we'll have a show of hands in a moment when I've asked the question. How much do you think the mission cost the European taxpayer? And I'm including here the satellite, the instruments, the launch, the operations, the ground systems, you know, so the data processing on the ground, all of that together. How much do you think it costs the European taxpayer?
Taxpayer.
Mm-hmm. So I've got a few answers for you, and we'll have a vote. Less than €1 per person. I'm talking about the whole cost over 16, 17 years. Collapsed, not an annual cost. 1 to 10, 10 to 100, more than 100 per person, per taxpayer. So have a think. Show of hands for less than 1. Yeah, few. Yeah, okay. I won't count you, but 1 to 10. Any votes for 1 to 10? Yeah, a few more, I'd say. Okay, 10 to 100. Anyone in the 10 to 100 camp? Yeah, a few less. Oh, you're an astute bunch, aren't you? And more than €100 per person? No, no one at all. Well, I'm pleased to report it's about €2 per person. Yeah, so it's the one I think most of you went for. So,
Including us.
Congratulations.
Including us.
Including you. Yep, you're paying tax, madam, yes.
Okay.
So anyway, I'm going to stop at that point and invite you to ask any questions. Yes.
No, the total cost. What was the
Total cost.
The total cost for the European part is about €850 million, and about 50% of the satellite and 50% is the launch and the ground.
Close to 300 million in European block, and if I thought €1 each, that would be 300 million, but you're saying it's 300 million.
More than 300 million.
I mean, this is rough and ready. I've said the population is 740 million for all the European countries combined, and I've said the taxpayers is something like half of that, 54% is a UK ratio. Not everyone's a taxpayer. Particularly the little people and the very old people. Anyway, well, thank you for your attention. So yes, so you have to you make a commitment to build something, and you have to freeze your design, and you have to say, right, I'm going to use these parts. These, when I say these electronic parts, because that's a large part of the cost is in the electronics. These parts have already had to go through a series of tests. So they've probably been frozen even early, a few years before that, in order to complete all their testing to be able to be used on a project like this. So yes, there's a lot of, if we did it now, it would look completely different in terms of processes and so on. But, you have to build it and then maintain it. And that's often quite difficult. Also, over the life of this project, I mean, I was the only person who was the project manager on this part of the satellite, but we had probably 3 or 4 people who were in charge of the satellite over that period, and 3 or 4 people who are in charge of the other instruments. And the staff change, of course, the engineers who designed it at the start, some of those have retired now. So you have to have everything documented to quite a level of detail, and the understanding documented as well of the design.
The whole thing seems awesomely complex in its early stage, and that you're having to plan a satellite like this with a vast range of different specialist skills. And somehow there has to be some team that can pull all this together, and it's just beyond me how you.
Was that you?
Well,
No, the different skills. I mean, the different parts, different skills.
It's a challenge, and that's one of the things that makes it an exciting thing to do as a professional engineer.
Yeah.
Okay, we're just going to have one more question because there are food waiting outside.
That's why
When
we're here.
EarthCARE's life is finished, it will presumably just carry on. Will it come back to Earth?
Yes.
Will there be any possibility of actually recycling anything from it?
No, it'll be it'll undergo a controlled deorbit.
Yeah.
All spacecraft now, before they're launched, have to have a plan for deorbiting them, so they're not leaving space junk in space. So it'll come down and burn up in the atmosphere, and anything large enough to hit the surface will have to end up in the Pacific, usually the South Pacific, the dumping ground.
Yes.
Okay, well, thanks very much, Nigel, for an excellent talk. See you in January for the Ediacaran fossils, and food is that way.